There we go. You can take a look at the inside of this. See, there's the two silver cesium plates, and then the anode wire is barely visible. It appears more as a shadow, but there's two anode wires basically right there that go up to collect off of these plates. So it's a completely balanced arrangement. We're using this as a Farnsworth multipactor tube, and the anode wires typically are not used except for as a remote source of excitation. So we'll go back over to the setup here. Now, we've been doing a lot of experiments to build a detector of bioenergetic fields, or what some people would call an orgone detector. We haven't with anything solidly conclusive yet, but nevertheless we are getting readings and responses. So the apparatus is brought to a power level to keep this thing operating at the necessary threshold. I can pick this photo tube up, and of course when I shine the light on it, it tends to move around and respond. But when I put my hand on it, you see the meter jumps right up. So we're getting close to what we want here. We have to work more with thresholds and build our own tubes, but of course we're working all with junk parts. By the way, these parts are all found at ham fests and in surplus stores and garbage cans, and sometimes you can find the stuff laying in the middle of the street if you're lucky. Now what we're going to do is change our setup here a little bit. Connect this as a regular photo tube and remove our source of excitation. And if we can see, the Simpson shows that we got a slight response from the fluorescent lamp.
You're right in front of the meter, so I can't show both.
There we go. We got a little bit of response from the room illumination, which is pretty bright for the videotaping purposes. Now I'm going to bring the intensity of our apparatus up here to a point where we get some reasonable output. And we can see that the phototube responds quite readily to the longitudinal dielectric induction existing at the end of this, primarily due to the presence of ionized gas. Get behind here so you can see the meter. See, it just jumps right up. Even though the illumination by the gas in there is barely visible, and of course I have a big 750 watt bulb hanging right up there on the ceiling, and that produces hardly any output at all. Now we'll go back to the board and do a little brief description of what multipactor action is all about. This was something discovered by Philo Farnsworth around 1930. He developed a whole series of tubes based on this principle that eventually led to practical nuclear fusion. Totally electronic, required no large magnets or lasers, and the thing basically occupied a space of roughly 10 cubic feet and produced 100 kilowatts of direct current, 1 ampere, 100 kV, for about 5 minutes before the little electrode screens inside the tube would melt. Going back to the original photo multipactor, what happens is something will dislodge an electron from the plate, which will fly off and then be attracted to the other plate. The little high-frequency oscillations of the wiring will produce jittering. And this electron flies off, hits the other plate, will knock more electrons off, which will fly around and go back to the other plate and knock more electrons off until eventually you can build up very powerful UHF oscillations with these things. The reason Farnsworth developed this tube was at the time the tetrode vacuum tube had not been developed yet. And being Farnsworth was in the process of inventing television at that time, he needed very high gain, high impulse response, or you might say wide band amplifiers, and he just couldn't get that out of the old triodes. So he decided to abandon the hot cathode grid tube completely and came up with this photo multipactor tube, which now in its final form that's available as today is known as the photo multiplier, which many people are familiar with and forms the heart of every television camera. Television camera tube, of course, being invented by Philo Farnsworth, as many know. Our dielectric induction detector was basically this down here, using this multipactive process to provide roughly a gain of about 60 to 70 decibels, so that the slight amount of ionization produced by the induction produced a significant response on the meter. Now, of course, we hook this to a tank circuit tuned to the appropriate transit time frequency. This effect will be magnified even more, and gains of 120 decibels are possible with a single tube. Now, we're going to get into some maybe practical connections of this circuit and a few other things, and that'll be pretty much it for this demonstration. So we have a few things here to consider and possibly experiment with. Now in industrial electricity, we have a situation where if we have a large system of motors, which require, of course, electrical energy and magnetizing energy, that the magnetizing energy and electrical energy have to be transmitted through the TEM line to the motor, resulting in two waves which tend to overheat the lines and drop the voltage. And normally what's done is a dielectric inductor or capacitor is hooked across the motor to provide the magnetizing energy, because capacitors will generate magnetizing energy, and that relieves the transmission line of the duty. And further, the magnetic induction, which is the prominent element in most transmission lines, being that the voltage doesn't operate much above your low voltage points, usually less than 66 kV, which most feeder lines are, you don't have enough dielectric induction for them to be anything more than an inductance coil. So it's just like a big transformer winding. The capacitor will resonate with this magnetic energy in the wire and cause the voltage of the system to raise as you go to the load, which of course is quite different than in normal DC circuits. So it's not uncommon in an alternating current power system that the voltage will start off nominal at the generator, which is usually 13.2 kV, and go up to 13.8 or 14, and if you remove the motor, it would go up to infinity. What happens when this is done, when the voltage gradient raises at the plant, the kilovolt ampere reactive hour meter will start to turn backwards, which usually causes trouble with the power company. Okay, now there's a new way to correct this, and we haven't performed all the experiments yet, but we're just starting on this. It's kind of hard to work with large power lines and factories and stuff like that, because usually they don't want to give you permission to go in and monkey with their stuff, not alone getting it to conform to the National Electric Code. But in other countries, of course, it's possible to do this without the restriction, and laboratory analogs can be built up the whole way, and it can be completely computed on the workbench. So in this case, what we do is build an LMD analog which conjugates or is in conjugation with the TEM transmission line to neutralize the transmission effect completely, rendering the motor and generator as one apparatus. Now this is still a theoretical type of situation, but nevertheless our mathematical and physical studies show that it's quite possible to do this, and we're getting ready to perform these experiments, and of course the information will be released in video and written form when we're done. Another thing is an LMD network is an analog of an organ pipe, and it will produce a complex harmonic spectrum rather than a single sine wave frequency that you conventionally get out of the LC oscillating circuit, or again the single repetition rate frequency that you usually get out of your RC networks, which contain harmonics that usually are not what you find in natural musical instruments. So a negative conductance, which may be a cathode follower with a capacitor in its cathode, or the capacitance of the line producing negative transconductance and oscillations. It could be a Hartley oscillator, it could be a photomultipactor tube. There's many different ways to produce negative conductance or resistance. This is connected to one end of the line to maintain the harmonic oscillations in the line. And then the dielectric end is very lightly coupled to an amplifier, which of course produces the sound in the speaker, and your musical keyboard of course would switch these things in as necessary to produce the music. So these are some things that the experimenter and the industrial engineer can consider in using these things for practical advantages, and of course they do produce very high voltages and Tesla coil effects without the high frequencies and interference with other services, which of course would get one in trouble with the FCC. So that wraps up our presentation of analog networks and the comparison of transverse and longitudinal energy flow in general. And I'll turn you back over to Tom Brown, Director of Borderland Sciences, to give a conclusion on our...
Thank you, Eric, for that very practical demonstration of the difference between transverse and longitudinal waveforms. Something that you've brought to the lab bench, and now we can understand it in very real forms, and the experimenters around the world can try these things for themselves and thereby carry on the works of Nikola Tesla, Charles Steinmetz, Philo Farnsworth, and of course yours, Eric. We must point out here, Eric, that on this date here, January 25th, 1988, here we see Eric going to a cloud of dust. He's been found in violation of the universal speed limit of 186,000 miles per second But as we know, this speed limit has been set by modernistic science, which has gone into realms of abstraction far beyond the practical realities of actual work in the lab. So we just want to thank you for watching, and we wish all of you out there good day and good science.